Welcome to lecture 13. This is week 3 and we are talking about basic concepts of optimization part 1. In the previous lecture, we have introduced certain concepts, we have introduced certain definitions such as unimodal functions, multimodal functions, concave convex functions, etc. In today's lecture, we will talk about optimality criteria for single variable unconstrained functions. So, there are two important terms here. First, the function we are talking about are single variable function and unconstrained, meaning there are no constants. So, in today's lecture, we will talk about the optimality criteria for single variable unconstrained functions. Later on, we will see unconstrained multivariable functions. And in the following week, we will see what are the optimality criteria for constraint functions, multivariable constant functions. So, in today's lecture, optimality criteria for unconstrained single variable functions. So, let us first introduce another definition known as monotonic functions. A function f x is monotonic, that means it either increases or decreases continuously. So, increasing function or decreasing function, if for any 2 points x 1 and x 2 with x 1 less or equal to x 2, it follows that f of x 1 is less or equal to f of x 2, then it is monotonically increasing. In other words, a function f x is monotonically increasing if you take 2 points x 1 and x 2 such that x 1 is less or equal to x 2, then f of x 1 is less or equal to f of x 2. In other words, as we increase from x 1 to x 2, the function value also increases. So, this is monotonically increasing function. The reverse is monotonically decreasing functions. So, if I take 2 points x 1 and x 2, as I increase from x 1 to x 2, the function value decreases. So, in case of monotonically increasing function, the function value increases as I increase the independent variable. In case of monotonically decreasing function, as I increase the independent variable x, the function value keeps on decreasing. It may remain constant. So, that is why less or equal to or greater or equal to. The function f x is unimodal on an interval a to b if and only if it is monotonic on either side of the single optimal point x star in the interval. So, let us consider this function f x. You have a single optimal point x star. From the figure, we know this is the minimum point. Let us say we are talking about the interval a to b. The function f(x) also you know now it is unimodal. We have talked about what is unimodal in the previous lecture. That unimodal function will have single minimum as it is shown in this figure. We are talking about minimum. Now, if you look at this side, that means on the right hand side of the minimum point x star, as x increases, the function value also increases. So, monotonically increasing. Now, if you look at the other side, that means the left hand side of the point x star, as the x increases, the function value decreases. So, the function f(x) is unimodal on the interval a to b if and only if it is monotonic on either side of the single optimal point x star in the interval. So, you can see on the right hand side of the x star, the unimodal function as shown in the figure is monotonically increasing, and on the left side of the minimum point x star, the function value is monotonically decreasing. Now, let us formally define what we mean by global and local minimum. The definition also applies to global and local maximum. We have mentioned in our previous lectures then the global optimal or the global minimum is the best minimum in the entire interval, and the local minimum is the best in the vicinity of the point we are talking about. Similarly, the local maximum is a point where the function value attains maximum in the surrounding of the point we are considering. But the global maximum refers to the point where the function value attains maximum considering the entire interval over the or entire domain over which the function is defined. So, let us now formally define what we mean by local minima or local maxima and global minima or global maxima. A function is said to have a relative or local minimum at x equal to x star if f of x star is less or equal to f of x plus h for all sufficiently small positive and negative values of h, that is in the near vicinity of the point x. So, if I take a point x star in the domain over which say the function value is defined, let us say this is the domain over which the function f x is defined. If the function value at x star is less or equal to f of x plus h for all sufficiently small positive and negative values of h, that is in the near vicinity of the point x, then x star is known as local minimum or relative minimum. That means, if I consider this as the near vicinity of x star, within this ball or the circle that I have shown using dotted lines, the function value will be minimum. Similarly, x star will be maximum, local maximum or relative maximum if f of x star is greater or equal to f of x plus h for all values of h sufficiently close to 0. So, in this region, if x star corresponds to the point where function value is maximum, then it is a local maximum or relative maximum. But let us say I have a point here x star where the function value attains minimum when you consider this entire domain, then this is local minimum. If this corresponds to the point where function value attains maximum, then this becomes the global maximum. So, the global minimum or global maximum is the point where the function value attains minimum or maximum when you consider the entire domain over which the function value is defined. So, a function is said to have a global or absolute minimum at x equal to x star if f of x star is less or equal to f of x plus h for all x in the domain over which f x is defined. So, now x is not defined in the near vicinity of x star, x is now over entire domain. Similarly, a function is said to have a global or absolute maximum at x equal to x star if f of x star is greater or equal to f of x plus h for all x in the domain over which f x is defined. So, the figure shows some of the local and global optima. You have these maximum points. You can figure out that this is global maximum. These are minimum and this is global minimum. So, this is a multimodal function showing several local and global minimal and maximal points. Now, we will introduce a theorem known as Weierstrass theorem, which talks about existence of a global minimum. If f x is continuous on a non-empty feasible set S that is closed and bounded, then f x has a global minimum. So, it is very intuitive. What the theorem says is, if a function f x is continuous on a non-empty feasible set S that is closed and bounded, then f x has a global minimum. The important words to note here is the feasible set S is closed and bounded. So, the continuous function on a non-empty feasible set S that is closed and bounded, f x definitely has a global minimum. Now, we will introduce the concept of necessary and sufficient conditions. So, we need to understand what we mean by necessary conditions and sufficient conditions before we talk about what are the necessary conditions of optimality and what are the sufficient conditions of the optimality. So, necessary conditions and sufficient conditions are general mathematical terms. So, here we will explain the necessary conditions and sufficient conditions in the context of optimal solutions or optimization. So, what do you mean by necessary conditions? The conditions that must be satisfied at the optimum point are called necessary. The conditions that must be satisfied at the optimum point are called necessary. If a point does not satisfy the necessary conditions, it cannot be optimum. Satisfaction of a necessary condition does not guarantee optimality of the point. So, the conditions that must be satisfied at the optimum point are called necessary. If a point does not satisfy the necessary conditions, it cannot be optimum. But if a point satisfies the necessary condition, the optimality is not guaranteed. So, what it means that there are situations where the necessary conditions are met at a point, but that point may not be optimal. But if the point does not satisfy necessary conditions, the point cannot be optimal. But satisfaction of necessary condition does not guarantee optimality. So, what is sufficient conditions? If a candidate optimum point satisfies the sufficient condition, then it is indeed an optimum point. If a candidate optimum point satisfies the sufficient condition, then it is indeed an optimum point. If the sufficient condition is not satisfied or cannot be used, we may not be able to draw any conclusion about the optimality of the point. So, remember, if the sufficient condition is not satisfied or cannot be used, we may not be able to draw any conclusion about the optimality of the point. So, now we will introduce the first order necessary conditions for optimality for unconstant single variable optimization problems. So, the conditions we are going to talk about are first order necessary conditions for unconstant single variable optimization problems. If a function f x is defined in the interval a to b and has a relative minimum at x equal to x star, where x star lies within a to b, and if the derivative df dx exists at x equal to x star, then the value of the derivative at x star is equal to 0. So, what it says is that if a function f x is defined in the interval a to b and at x equal to x star a relative minimum occurs, this x star lies within a to b, and if the derivative df dx exists at x equal to x star, then f prime x equal to 0. So, let us say this is the function single variable function. Let us say this is a and this is b. So, the function is defined in the interval a to b, and if you say at x equal to x star so this is x star. There exists a relative minimum, then if df dx exists, so the df ds at x star will be equal to 0. This is also written as f prime x star equal to 0. So, this is the first order necessary conditions for optimality. A relative minimum f prime x star will be equal to 0, but we have more to say about it. The theorem does not say that the function necessarily will have a minimum or maximum at every point where the derivative is 0. The reason is, if you have a function like this in the interval say a to b, here it attains a maximum, here also f prime is equal to 0. The derivative here is also 0. So, in general, a point x star at which the derivative is equal to 0 is called a stationary point or a critical point. A stationary point can be a local minimum or it can be a local maximum. It is also possible that a stationary point will be neither minimum nor maximum. In such cases, such stationary points are known as inflection point or saddle point. So, what we learned about the first order necessary theorem, first order necessary conditions for optimality is the derivative, the first derivative will be equal to 0. So, if you have a function f x, x is a single variable f x, df dx at x equal to x star is equal to 0, where x star is known as stationary point. Now, this stationary point can be a minimum, this stationary point can be a maximum. It is also possible that this stationary point is neither minimum nor maximum, it is an point of inflection or saddle point. So, the first order necessary conditions for optimality is df dx equal to 0 at the stationary point. So, df dx equal to 0, if you solve, you will get the stationary point. So, that is a likely candidate for minimum. Next, let us talk about second order necessary and sufficient conditions for optimality. Again, we are talking about unconstant single variable optimization problems. So, if a function f x is defined in the interval a to b and has a stationary point at x equal to x star, then the second order necessary condition for local minimum is second derivative is greater or equal to 0. So, d square f dx square is greater or equal to 0. Second order necessary conditions for local maximum, d square f dx square is less or equal to 0. So, first order necessary condition was df dx equal to 0. It may either be minimum or maximum. So, second order necessary condition for local minimum is d square f dx square is greater or equal to 0. Second derivative is greater or equal to 0. Second order necessary condition for local maximum, d square f dx square is less or equal to 0. Now, let us talk about sufficient conditions. So, second order sufficient condition for local minimum is d square f dx square is greater than 0. Similarly, second order sufficient condition for a local maximum is d square f dx square less than 0. So, df dx equal to 0 gives you the, if df dx equal to 0 is the first order necessary condition and gives you the stationary point. If d square f dx square at x star is greater than 0, then that is sufficient to tell that the point x star is a local minimum. Similarly, if d square f dx square is less than 0, you can say that the point is a local maximum. But what happens if d square f dx square equal to 0? See, this is included in the second order necessary conditions. If d square f dx square is equal to 0, again you cannot say anything about the optimality, with meaning that we cannot be sure whether the point is minimum or maximum. So, what do? We look for higher order sufficient conditions. So, we will go on taking derivatives until we get the first non-zero derivative. So, next let us talk about higher order sufficient conditions. So, we are talking about a situation where df dx equal to 0, first order necessary condition. Second, d square f dx square is also 0. So, we are talking about a stationary point at x star. So, definitely at x star df dx equal to 0. If the second derivative is greater than 0 or less than 0, we are sure sufficient conditions are met and we can say it is minimum or maximum. But if second derivative d square f dx square at x star is also 0, then we cannot say anything about minimality or maximality. Whether the point is minimum or maximum, we are not sure. So, we go for higher order sufficient conditions. Here what we do is we go on taking higher order derivatives, evaluate the derivative at the stationary point x equal to x star and look for the first non-zero higher order derivative. Look at the order of the derivative. If that is even, it is either minimum or maximum. If this is odd, that is point of inflection. So, minimum or maximum will depend whether the derivative is positive or negative. If the first non-zero derivative is positive and the order of the derivative is even, the point is minimum. If the first non-zero derivative is negative and the order of the derivative is even, you have the local maximum. So, formally let us say that we consider f prime x star, f double prime x star, that means second derivative. We go on taking derivative unless we get the first non-zero derivative. Let us say the first non-zero derivative, the order is n. So, if n is even, then the point x star is either a local minimum or local maximum. If the derivative is positive, it is a local minimum. If the derivative is negative, it is a local maximum. But if n is odd, then the point is neither minimum nor maximum, it is a point of inflection. So, let us quickly take two simple examples. Find the optimum value of the function f x equal to x square plus 5 x minus 2. Does the function attain a maximum or a minimum? So, take first derivative and set equal to 0, because that is the first order necessary condition for optimality. So, we take df dx and set that equal to 0 and get x star equal to minus 5 by 2. Now, the question we ask is x star equal to minus 5 by 2 is minimum or maximum? So, you need to take second order derivative. So, d square f dx square equal to 2, which is greater than 0. So, since the second derivative is positive, the point x star equal to minus 5 by 2 is the minimum point, and the function value attains a minimum value of minus 33.4 at this point, that you can find out once you put this value in this function. Let us take another function y equal to f x equal to x s cube. So, y equal to x s cube, the plot is shown. Is the origin, that means x equal to 0, a maximum point or a minimum point or point of inflection? the first derivative y equal to x cube, first derivative of y equal to x cube is dy dx equal to 3x square. So, at x equal to 0 it is 0. The second derivative is 6x. So, at x equal to 0 both df dx equal to 0 as well as d square f dx square equal to 0. So, you cannot make any comment at this stage. So, we need to take the higher order derivative. So, y equal to x cube df dx was 3x square, d square f dx square is 6x. So, d cube y dx cube equal to 6. This is non-zero. So, first non-zero derivative is d cube y dx cube. So, third order derivative. So, 3 is odd, that means n equal to 3, it is odd. So, in the previous criterion of optimality, you have seen that if n is even, then only the point may be minimum or maximum, but if n is odd, it is a point of inflection. So, the point x equal to 0, that is origin, represents a point of inflection. It is neither minimum nor maximum. So, with this we will stop lecture 13 here, and in the next lecture we will talk about the proof of this optimality condition for single variable unconstant function.